Okay, so the very last talk of the workshop will be given by Bartomeu Monserrat, and it will be about the Phonon-Phonon interactions and charge density waves.
Thank you very much to Ron for the introduction. And I must first apologize because I missed most of the meeting because I could only make it here yesterday. But it's definitely been worth it to catch up with some of you and hear at least one talk other than mine. And I should also start with a disclaimer, which is that Kagome materials are a bit of a new topic for me. So this is more of an experiment rather than me being a true expert. And my angle is from a first principles perspective. So I usually calculate the properties of materials. And the reason why we got into this topic is because first principles methods are heavily used to understand potential ordering wave vectors and span structures and so on. And as I'll show with an example, sometimes the accuracy of these methods can be somewhat questionable, and we always need to be somewhat critical of how accurate DFT can be. And I just want to discuss some of these ideas. And as part of that, I'll try to argue that Phonon-Phonon interactions, which are typically neglected in DFT calculations, can make a big impact in understanding this type of materials. So to get started, I just want to make sure we're all on the same page. So I'll say some very, very simple things about phonons and structural distortions. And I just want to start with the ionic Hamiltonian, which describes the motion of ions in my crystal after I've applied the Born-Oppenheimer approximation. On the one side, I have the electrons, which is what we typically get from DFT. And then on the other side, I have the ions. I have a kinetic energy term and the potential energy term, which we call the Born-Oppenheimer energy surface. And this potential energy term essentially depends on the ionic configuration U. And at each configuration U, its value corresponds to the electronic energy of the system for that ionic configuration. So in principle, you can, for example, map this potential energy landscape by looking at different atomic configurations and solving DFT, say, for each of those. Now, in practice, that's very, very difficult to map. So what we do is we apply the harmonic approximation, where we expand this potential energy landscape about some reference configuration, typically the equilibrium configuration of the system, such that you have no linear order term, and then the second order term looks like this. There are many, many indices here. Don't worry about them. In a crystal, we have to worry about which cell in the crystal we have the atoms, what atoms in the bases we look at, and what are the XYZ coordinates that we displace the atom along. But in practice, all this is the Hessian of that function. And then we just make a change of coordinates to the normal mode basis, and we end up with a typical harmonic Hamiltonian in terms of these uncoupled phonon modes labeled by wave vector Q and branch nu. Again, there are all these sort of labels that we need to keep track of to make sure we describe all degrees of freedom in our system. But in practice, what this harmonic Hamiltonian does is very, very simple. The key quantity is the frequency squared here, which measures the curvature of the potential near equilibrium. So here I have two examples, one where omega squared will be large. I have a large curvature in my potential, and one where omega squared may be a bit smaller. So I have a shallower curvature in my potential. That's all there is to this quantity. And of course, the square root of this eigenvalue gives me the phonon frequencies that we're all familiar with. So we can do these calculations for phonons in a wide range of materials using different methods. Here at the top, I have an example of diamond, which is a well-known, very simple material, where doing DFT phonon calculation gives you good results. At the bottom, I have a slightly more complex one, which is high-temperature paramagnetic iron, which DFT struggles somewhat to get because the paramagnetic state is difficult to capture in DFT, but one can use something like DFT plus DMFT to describe the electronic structure and then again calculate the phonons for those. And both of these examples correspond to a situation where the eigenvalues of my Hessian are positive, and that leads to real and in fact positive phonon frequencies. And that means that we're near a minimum, so the structure is dynamically stable. However, there are some examples, and I'll talk more about this later on, but one of them is this Kagome bilayer, scandium vanadium tin, where if you do this phonon calculation, what you find is that there are some modes which have imaginary frequencies. And the reason why you have imaginary frequencies is because the Hessian has negative eigenvalues, so omega squared is negative, and that gives you imaginary frequencies. Typically, you'll see them plotted as sort of negative values, but in reality, that's because we cannot, it's harder to plot otherwise. So, but in reality, what these mean, these negative values mean, are imaginary frequencies. And they're very, very interesting for a charge density wave perspective because they tell you which direction to take, in a sense, in configuration space to lower the energy of your system. And that's sort of a distortion that you can put through your system to lower the energy, and that's what may drive, say, a charge density wave. So in order to fully characterize these systems where you have negative eigenvalues for the Hessian or imaginary frequencies, the harmonic approximation is not enough, because the harmonic approximation just looks at the curvature near the reference structure, if you want. So what you need to do is you need to go beyond this harmonic approximation. And here you have a simple model where I look at the quartic potential. So I have a harmonic term and then a fourth order term. And I focus on an example where omega squared is negative. So I have this typical double well potential. And essentially, if you do a phonon calculation for this reference structure, you will find some negative eigenvalues or imaginary frequencies that will take you, the associated eigenvectors will take you all the way down to these nearby lower energy configurations. Something that's very common, again, very well understood, is that this potential energy surface, of course, corresponds to the zero temperature limit, if you want. But when you include vibrational entropy to the problem, then you no longer care about the potential energy surface, but you care about the free energy surface. And that free energy surface changes as a function of temperature. And in particular, it may become stable, or the frequency may become positive with increasing temperature. And there are many ways in which one can describe this, but in practice, if we want to describe this combined with DFT calculations for real materials, this becomes extremely challenging to do. So only in the past 10 years or so have realistic methods to accomplish this become available. And perhaps the simplest you can think of is what's called the self-consistent harmonic approximation, where you try to find the best, essentially you try to minimize the free energy with respect to a harmonic trial wave function. And if you do that for this very simple quartic potential, that's the answer that you get. You get that the effective frequency, the effective anharmonic frequency at a finite temperature is given to the bare frequency and then this temperature-dependent correction. And that can lead to this sort of a temperature-driven change in the potential. So it's very, you can get this closed form expression if you want for this simple potential. In a real system, we'll have many, many degrees of freedom, and the potential may not look as simple as this. So that's what has been challenging to do in the context of first principles methods, but it has become possible in the past few years. There are a number of strategies to do that. They mostly rely on this self-consistent harmonic approximation, where again, you optimize the ionic wave function to minimize the free energy. And the difference between the different methods mostly boils down to how do you sample this full energy surface, and the method we're going to use uses stochastic implementation of the self-consistent harmonic approximation to sample that. Okay, so that was sort of the laying out the stage, and now I want to look at an illustrative example of how we can use these ideas to better understand charge density waves, and I'm going to use the bilayer Kagome metal scandium vanadium tin to do that. So that's the structure for this compound at high temperatures, and it's a hexagonal compound. It has two Kagome layers with the vanadium atoms in red and tin atoms, which I label tin 1. So there are three different tin sites in this structure. So the tin 1 are the ones in the Kagome layers. Then there's also a triangular layer of scandium atoms in purple and these tin 3 atoms, and then a honeycomb layer of what are called tin 2 atoms. And what will be relevant for our discussion of the charge density wave are these chains here of tin-1, scandium, tin-1 atoms. So there is a growing number of experimental work on these compounds, and there is perhaps the original one where they identify a charge density wave transition from this high temperature phase to a charge density wave state below about 92 Kelvin, and the ordering wave vector is what I call here Q3, which has coordinates 1/3, 1/3, 1/3. So there is a modulation in plane and also modulation out of plane. And the modulation I'll mostly focus on is the out of plane one, because that's the one that's perhaps a bit controversial, as we'll see in a moment. But what this out of plane modulation essentially means is that these ions I highlighted earlier at the edge move with a modulation of 1/3. And I'll look into that in a bit more detail later. And other experimental work suggests that there are actually competing charge density waves in this compound. For example, this is results from elastic X-ray scattering, where they observe phonon softening at two different wave vectors. So one of them is this third, 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 but they also observe softening at the wave vector, which I label Q2, third, third, half. So again, they have the same in-plane modulation, but distinct out-of-plane modulation. So although the ground state experimentally, the agreement is that it's driven by this wave vector, there seems to be some perhaps short-range order with this other wave vector developing before the full charge density wave transition to the Q3 order. Now, on the theory front or on the calculation front, there are many works, and I've just picked this one because it's one of the early ones and very insightful comments. But I could have picked many others to show very similar results. Essentially, if you do a phonon calculation, you get this type of band structure where you see, again, these negatives here just mean imaginary frequencies. And what you see are, in fact, many imaginary branches in, well, an imaginary branch that spans a large fraction of the reciprocal space. And then what they also did was to follow the eigenvectors associated with the dominant instabilities here and to map their energy as a function of ionic displacement. And in doing that, what you find is that what DFT predicts is that the lowest energy structure of this compound actually corresponds to the Q2 distortion that has a modulation of 1/2 in the out-of-plane direction, rather than the Q3 distortion that is observed experimentally. So this is a clear disagreement between theory and experiment. And that's one of the motivations that we had when trying to understand this system. So, and part of it is just to assess how reliable DFT can be in studying this cloud of systems, because you can see these energy differences are very small between all these different potential distortions. So, are we reaching the limit of what we can reliably calculate? And if so, what is the best approach we can take to make some sense of this type of results? So now I want to discuss some of our calculations on this compound. And the first idea I want to discuss is the role of the out-of-plane lattice parameter. So now these are our calculations. So these are our harmonic phonon calculations, which again give results which are very similar to those published previously by other teams. And just to make things a bit clearer, the way I'm showing this is in this first diagram, I'm showing the typical Brillouin zone path that is shown for hexagonal structures, where you first go around the loop in the kz equals 0 plane, and then you go to the kz equals pi plane, and you do the similar loop up there. And you see that the instability at the H point here corresponds to this 1/3, 1/3, 1/2 wave vector that experimentally seems to compete with the true charge density wave order, and theoretically is predicted to be the lowest energy configuration. And then if you do another loop at this particular wave vector shown by dotted lines here, which corresponds to a kz of 1/3, then you find this k prime point which corresponds to this Q3 wave vector, that does also appear as unstable in the calculations, but it's the one that dominates experimentally. So to look at what they look like in a bit more detail, again, they both have a third distortion in plane, but the key difference is what happens in the out-of-plane direction. And to understand that, we need to look at this tin-1, scandium tin-1 trimer that I highlighted earlier. Essentially, in the Q2 distortion, this trimer moves out of phase with the trimer right next to it, and that gives you the size 2 modulation. And in the Q3 distortion, you have a threefold modulation, if you want, where one goes in one direction, one goes in the other direction, and one sort of in between. So you have this threefold modulation. So the key difference is between these two potential modulations. So first about the accuracy and role of DFT. So when you do a DFT calculation, really you can get any answer you want. There's plenty of functionals one can choose from. There's plenty of approximations that you can make in there, and you can pretty much get any answer you want. So, what we think is important is to understand when you change the level of approximation that you use in DFT, what is changing in the crystal that may determine the results that you get, the answer that you get. And what we think is critical in this system is essentially the C-lattice parameter. And it's really easy to understand why that's the relevant quantity. So this is the structure, and the Q2 wave vector corresponds to these two trimers going against each other. And the Q3 structure corresponds to a group of 3 trimers oscillating with a modulation of wave vector 1/3. So in a sense, this vibration needs more space than this vibration for it to be accommodated in the structure. An example of what you can tweak in the DFT is how do you describe your valence and core electron states. So in typical pseudo-potential DFT calculations, what you do is you select a subset of your electron states that you treat as core, and then you really only describe the chemical bonding and so on of what you call the valence states. But you have a choice as to whether you set that boundary between core and valence states. So in this particular example, if you use the standard choice, which I call no semi-core states, so few valence states and quite a few states in the core, then you find indeed that the Q2 distortion dominates, like previous studies showed. But then if you include more states in the valence, that's what I mean here with semi-core states, you actually find that the Q3 distortion dominates. And the reason for that essentially is because when you have these extra semi-core states, the structure changes a little bit. So the C-lattice parameter shrinks a little bit. That means there's less spacing between neighboring trimers, and therefore that favors this distortion, which needs less space for it to occur. So again, I make a slightly different choice of DFT model, and I get a different answer. And one could argue this should be more accurate than this because I have more states that I explicitly calculate in the valence. But that still doesn't make me feel very comfortable. What makes me feel more comfortable is to look at trends. And trends are perhaps more reliable than otherwise. And I think the message here is that the C-lattice parameter is what dominates the physics. So what we can do, for example, is to build a phase diagram where we look on this axis at the out-of-plane lattice parameter C, and in this diagram at the in-plane lattice parameter. And then see, for example, what is the relative energy of these two distortions in this phase diagram. And what you do find is that the C-lattice parameter essentially controls which is the dominant distortion. And for small C-lattice parameters, you find that the Q3 distortion in red dominates, and for large lattice parameters, it's the Q2 distortion that dominates. And we can understand that because of the sort of twofold and threefold nature of these distortions. And then, yes, you can play around a little bit with the choice of functional, the choice of semi-core state, and so on, to fall in this regime or this other regime. And likely what happens is that experimentally, you really at the configuration here, and that's why you get a Q3 distortion. But it also tells you that you're very, very close to a Q2 distortion dominating. So a suggestion you can straight away make here is how could we drive the system to have a Q2 dominated distortion? And a suggestion we have is to apply in-plane epitaxial strain, which then in-plane compressive epitaxial strain, which then will expand the C lattice parameter, and that's what this line here indicates, and potentially drive you into this Q2-dominated regime. You can also look at how hydrostatic pressure, for example, could change things, and what you find is that hydrostatic pressure, we think eventually will just kill both charge density waves because it constrains that C lattice parameter and therefore avoids distortion. Okay, so that just to to a word of caution about the accuracy and limits of the FT and how perhaps best approach this sort of problems, which is look for general trends rather than specific results. But having established that we roughly understand what's dominating the behavior of the Q2 and Q3 charge density waves, I now want to discuss whether we can describe how these charge density waves develop in this system. And for that, we're going to study anharmonic Phonon-Phonon interactions. So again, this is a repeat of the calculation that I showed earlier, where I showed the harmonic Phonon dispersion calculated for the high temperature phase. And all I've done is I've zoomed into the regions of interest. So here I show the path along this dotted line, which corresponds to the Q3 wave vector, which is the dominant one experimentally. And here I'm just showing the path on the kz equals a half plane, which corresponds to the Q2 wave vector that competes with the Q3 wave vector, but eventually does not dominate. So one thing we can do is we can repeat those calculations, but now incorporating anharmonic Phonon-Phonon interactions using the methods I've described at the very beginning. And we can do that at various temperatures. And we see a few interesting things. So first of all, so the dark blue curve actually corresponds to 0 Kelvin. What that means is that so the reason why that's different from the harmonic approximation is because I do take into account quantum fluctuations. And that can make a difference. Well-known examples could be the quantum paraelectrics and so on. And in this case, it does make a difference. For example, the instability at the A point that is predicted at the harmonic level goes away entirely, even at 0 Kelvin. So again, that somewhat limits the problem. At the harmonic level, there are many potential instabilities. If you do a more accurate calculation, including anharmonic terms, many of them go away. But you are still left with the dominant ones, the K prime or Q3 instability, the Q2 instability, and then also at 0 Kelvin, you have a tiny instability at L still. But then if you go to 50 Kelvin, the L1 also goes away, and you really only have the Q2 and Q3 instabilities. So this shows that indeed these are the two dominant instabilities in the system. And then what you see is that as you increase temperature, these instabilities end up going away. And interestingly, at 200 Kelvin, both of them are gone. At 100 Kelvin, the Q2 instability is there, and at 50 Kelvin, the Q3 instability is also there. So this seems to suggest that if you start from the high temperature phase, you first hit the Q2 instability, and then you hit the Q3 instability. So I don't want to say that agrees with the experiment, but experimentally you do see first the development of short-range Q2 order, and then the Q3 order dominates and takes over. So that's at least has the same ordering as that. We can track exactly at what temperatures this happen. We just plot omega squared. We do a linear fit into those to see how these two different instabilities soften. And we see that the Q2 instability in our calculations softens at 140 Kelvin, and the Q3 instability softens at 84 Kelvin. This is with this particular choice of parameters and volume. As I've seen, you can change these numbers somewhat by changing choices that you make in the calculations. But the important thing is that the softenings are not too dissimilar from the experimental results shown as these open squares, and they're of the same order of magnitude. I can play a little bit around with their precise values, but they're of the same order of magnitude, and they're very different to the sort of numbers that you get if you try to take into account only electronic temperature changes. If you do that, then you get things that are orders of magnitude away from the transition temperatures that are observed experimentally. And then, so this results suggest that for at least at the calculation level, first Q2 develops and then Q3 develops. And then here, I'm now showing the free energy difference between the two, again, as a function of temperature. And we do see that the Q3 distortion does end up dominating. And in our case, it's at 42 Kelvin. But again, we can change that number somewhat by playing around with our approximations. But again, at least it's of the same order of magnitude as the observed experimental ordering. OK, so I just thought, so that's all I wanted to really say about bilayer Kagome metals. But I thought I would have a few words about this completely different topic, just because this is an audience interested in Kagome materials. And I think Kagome materials could be quite good to explore this sort of physics. So I just thought I would take the opportunity to say a few words about that. So this refers to, so again, I'm changing topics completely now. So a bit of a switch here. But this concerns multi-gap Euler topology. And just a brief introduction into what I mean by that. So standard topology that you're probably familiar with, Weil semimetals, topological insulators, and so on. In this context is what I'm going to call single gap topology, where what you have in mind is you have some occupied bands, then a gap, and then some unoccupied bands. Maybe you have a few crossing points or lines between these bands. And in that context, I'm going to call that single gap topology. And ultimately, you can describe a lot of it as two-band model settings and so on. I want to contrast that with what I here call multi-gap topology, which has a number of features. The first one is that the minimal models that you need for these are three-band models, 1, 2, 3, and therefore you naturally get at least two gaps. And the second feature is that in these three-band subspaces, you can end up with real Hamiltonians. And that means you must have some symmetry conditions in your system to ensure that that's possible. And in this particular case, these are things like C2T or PT symmetry. The reason why I'm bringing this up is because the understanding the topology of these multi-gap phases is a little bit different to single-gap phases. So for example, if you have a band crossing in the context of single-gap topology, you would characterize that node crossing with the Chern number. You would say build a surface around that crossing point, calculate the Chern number, and see what is the charge, if you want, of that point. You can do similar things in multi-gap topology, but now remember you have three bands, say. And in this case, you can show that the crossing points are characterized by the quaternion groups, rather than having plus minus 1 values here. They have values that are elements of the quaternion group, and rather than characterizing them with the Chern number, you characterize them with the Euler class. And these gives these phases somewhat interesting features, perhaps the more interesting one of which is that you have this the possibility of non-abelian braiding in reciprocal space, in the bulk reciprocal space, because essentially the quaternion group doesn't commute. So in this particular setup, for example, I have this energy versus momentum of these crossing nodes. Here I have the same energy diagram, but now in the momentum K1, K2 space. And what I'm doing is I'm looping one node in one gap around the node in the other gap. And in doing that process, I flip the sign of both nodes. So that means in the initial configuration, these two nodes in green in the second band, or these two nodes in red in the first band, they had opposite signs. So if you bring them together, you can annihilate them in the usual way. But now after this braiding, I flip the signs of these two, but not of these two. And now I can no longer annihilate them because they have the same sign. So this could potentially lead to interesting features that are somewhat different to those of standard single gap topology. OK, so why Kagome materials? Well, Kagome materials very naturally give you three sites. And therefore, they give you a natural platform to end up with groups of three bands where you can explore this physics. So this is an example of some work that we did a few years ago now, where we looked at 2D Kagome material. And indeed, in this case, we looked at the phonon dispersion. The reason why we look at phonon topology is, again, because of this multi-gap nature, but you also have this in electron systems. And you can see very nicely that the choice of a Kagome material does lead to these groups of 3 bands and so on. And then you can zoom into those groups of 3 bands and explore this type of topology. And in this particular material, we do find that, for example, you can use an out-of-plane electric field to control the location of these band nodes, essentially to make them move around. And additionally, the symmetry of the system is such that these braidings that I was showing earlier in this particular symmetry setting all collapse to the gamma point. So the braiding eventually becomes just a band inversion at the gamma point, and you could, in principle, we think you could, in principle, track it, say, by following the evolution of the Raman spectrum of these nodes. So, as I said, a brief detour into this topic, just because we think Kagome materials could be important in that setting, because they naturally give you these 3-band models that are relevant for multi-cap topology, and this is a Kagome audience, so I thought I would bring this up. So to finish, we've looked at scandium vanadium tin, which has competing charge density waves. They're really, the energy differences are very, very small, so it's always hard to do anything reliable with, say, DFT in that context, but one can at least try to understand trends. And then I've also highlighted the importance in that context of the out-of-plane lattice parameter and anharmonic Phonon-Phonon interactions. Just to finish, to thank my team, the people who led the charge density wave Kagome work that I've described, and thank you all for your attention.
Thank you. We have plenty of time for questions. This might be the first session since Monday where all speakers have been more or less on time. So usually we always went over time.
Just a short question regarding your phonon spectra at the very end. You mentioned there are 3 bands appearing, but if I observed it correctly, there are also 2 bands appearing. Is that correct? Is this coming from the silicium, which are basically on a honeycomb lattice and then giving 2 bands?
Very possibly. I should check that. So I didn't focus on those 2. We just eventually to look at the topology.
I understand.
Very possibly. The other option is that for some reason they may be degenerate or something. But yeah. But I could look into that.
Short follow-up question. In this material, it's then just the energetics that does not lead to 5 bands to intersect.
I guess so. But you do have
Are there, I don't know.
So here, in this particular setting, you do have groups of 3 bands that are separate, but then you can actually play a little bit around with things like strain and so on to change things, such that you enter other regimes as you're highlighting. But literally, just to illustrate the point that we can naturally get groups of 3 bands that then we can exploit for this.
As a quick follow-up to Andreas' first question, is it possible that you have LOTO splitting and that splits the bands into 2, or is this actually a metal?
So in 2D materials, LOTO splitting doesn't actually split the bands. It changes. So this is a 2D setting, and what LOTO splitting does is it changes the slope of the branches when they approach the gamma point, but it doesn't actually split them in energy. So yeah.
Okay, I have a question about your, semi-core issue. I don't think it's surprising, in this kind of small energy scale. And of course, I really trust you very carefully attract that kind of, but I'm just out of curiosity. This material is also van der Waals interaction is involved, right? Is it true?
So
your material. That case.
So
yeah.
Just to answer, so the reason why the additional knot of semi-core states changes the answer is precisely because it changes the structure. So if you optimize the geometry of your system without semi-core states, you end up with slightly larger C-lattice parameter. And if you optimize it with semi-core states, not changing anything else, just changing semi-core states, you end up with a slightly smaller lattice parameter. And in this particular calculations, We use the PB solve functional if you want, and which is also what many other people used. And in that setting, that's enough to make this difference. But as you correctly say, in a sense, that's a detail, and the reason why I highlight this is because that's what most people use to do the calculation, and that's why most people got this as the ground state. But in reality, yes, what really controls the physics is the C lattice parameter, and there are other ways, other means by which you can change that. So van der Waals interactions would bind it further, so you would also go down this direction. If you use, say, a PB functional, you would go the other direction. And that's also what other people have done. So the point here was just to illustrate, that was just an example of the sort of changes that you can make to your system. But the key point I was trying to make is that these are all choices that we have when we do the FT calculations, and it's hard very often to decide that's the right answer and that isn't the right answer. But what matters is, can you understand why this is happening? And I think that it is the C lattice parameter that controls that.
Do you remember particularly which was the key semi-core state that need to be included?
Yeah, so I do have that. Let me very quickly, just to make sure. We did that for two elements, actually. And let me very, very quickly, just to make sure I don't say anything that's wrong, let me very quickly look it up. So the usual calculations for, the usual calculations that most people do for scandium, in the valence they include the 3d and the 4s orbitals, and for tin, the 5s and the 5p orbitals.
I see.
In our with semi-core states, what we did is for the scandium, we also added the 3s and the 3p orbitals, and for tin, the 4d orbitals.
Okay, so are you using some kind of non-conserving pseudopotential or ultra non-conserving?
Yes, so we try with both, and we actually also have cross-checked with all electron calculations. So yeah, we've done a lot more than what I'm showing here.
So basically, type of pseudopotential doesn't matter.
No.
Okay.
But again, you can find slight differences perhaps with the function that you choose and so on. So this is always tricky to say. But so we've tried many, many different things. That was just to illustrate the point that TFT calculations can be tricky and you can get any answer you want. But what I want you to take home from this is that it's the C lattice parameter that dominates that. And as long as you're in the right regime, then you can get the right physics. Yeah.
Thanks.
Yeah.
Speaking of things that can change the C lattice parameter, is there a reason to be worried about thermal expansion in the system? Does it change C appreciably in this plot?
Absolutely. So thermal expansion is, of course, something else that can do that, and we did include that in our finite temperature calculation. So, for example, these free energy calculations would be such that so when you do the self-consistent harmonic approximation, your variational parameters are in fact not just the wave function itself, but also the positions of the ions and of the lattice. So you can take into account fully thermal expansion. That's what we've done here. So I can't remember on top of my head those numbers in isolation, what they do, but in these calculations they are included.
But do you remember are they more on the negligible side compared to the Phonon-Phonon interactions?
I think so. I think so. Yes. Essentially, yes. Even if you fix the lattice parameter, you do see these transitions driven by Phonon-Phonon interactions. Yes.
Okay. So, thank you. Any other questions? Okay, then let us thank our speaker once again.